Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. In this session, we will discuss about the pin configuration of 8086 microprocessor. So before going to the pin configuration of 8086 microprocessor, we will see the features and then we will discuss about the pin configuration of 8086 microprocessor. Now, coming to the features of 8086 microprocessor, this 8086 microprocessor is the enhanced version of 8085 microprocessor. So, all the features compared to 8085, in 8086 microprocessor, the features will be advanced. So, here, when discussing the features of any microprocessor, we have to consider the features like the size of the data bus, so size of the address bus, what is the size of the memory. So all these features we have to consider. Now, coming to the 8086 microprocessor features. So in this, we have 16-bit data bus. Okay. So here, 16-bit data bus means the number of data lines available in 8086 microprocessor is 16. So that is why this 8086 microprocessor is called 16-bit microprocessor. Now, so this 8086 microprocessor is having 20-bit address bus. So the number of address lines available in 8086 microprocessor is 20. So that is why it is a 20-bit address bus. Now, the memory size available in 8086 microprocessor, there is physical memory available in 8086 microprocessor is 1 MB. So generally here we are going to have this 1 MB memory based on the size of the address bus. Okay. So here in the 8086 microprocessor, the address lines are 20. So in order to know the memory size of this microprocessor, you have to write this as 2 power 20. So here this 20 represents the number of address lines. So this will give the size of the memory. So the value of this 2 power 20, it is 1024 bytes. Okay. So it is nothing but 1 MB memory, physical memory size available in 8086 microprocessor. And next, it is having 14 16-bit registers. That means the number of registers available in 8086 microprocessor is 14 registers, and all the 14 registers, each register is 16-bit in size. So we have already discussed about what are all the 14 registers that are available in 8086 microprocessor while discussing about the register organization of 8086 microprocessor. Now, so it has multiplexed signals. That means it is having multiplexed address and data bus. So multiplexed lines means both the address and data will be provided by using a single signal. So that is what we call as multiplexed address and data lines. The same signal can be carrying the address and also data. So here the multiplexed address lines and data lines available in 8086 microprocessor is from AD0 to AD15. So in this here A represents address and D represents data. Here in 8086 microprocessor, the data bus width is only 16-bit. That is why during multiplexing, only the data lines from D0 to D15 are multiplexed with the address lines. But the address bus width in 8086 microprocessor is 20-bit. So that is why here the remaining address lines, that is after 15, which are multiplexed with the data lines, the remaining address lines are individual. They are from A16 to A19. They are not multiplexed. They are not multiplexed with data signals. Next. So it requires plus 5 volts power supply. So the power supply required for 8086 microprocessor is plus 5 volts DC supply. And next feature is, it is a 40 pin IC. And all the 40 pins are arranged in the dual inline package. So here dual inline package arrangement means 20 pins will be present at one side and the remaining 20 pins will be present on the other side of the IC. So this type is called arrangement of the pins. In this type, we call it as dual inline package. And so this 8086 microprocessor can be operated in two modes. So it is having two modes of operation. So what are the two modes here means? One is maximum mode and another mode is minimum mode. Okay. So what is meant by maximum mode means, maximum mode is suitable for a system having many processors. That is why this maximum mode is also called multiprocessor mode. And coming to here, the minimum mode. This minimum mode, it is suitable for a system having single processor. So that is why this minimum mode is called uniprocessor mode. Okay. So this maximum mode is called multiprocessor mode, whereas this minimum mode is called uniprocessor mode. Okay. So this maximum mode means it is suitable for a system having, so maximum mode now, so it is suitable for a system having multiple processors. It is suitable for a system having multiple processors. And whereas here in the minimum mode, this minimum mode is suitable for a system having single processor. Okay. So since it is a single processor, it is also called uniprocessor mode. It is capable of a system for having multiple processor. That is why it is called multiprocessor mode. So these are the two operating modes of 8086 microprocessor, that is maximum mode and minimum mode. Now, so here, because of that modes of operation, that is, since 8086 microprocessor is going to operate in single processor mode and multiprocessor mode, we can say that because of this, the high performance can be achieved. And next, 8086 microprocessor is capable of operating at a frequency 5 MHz, 8 MHz and 10 MHz. That means generally based on the 8086 microprocessor versions, that 8086 microprocessor is having the operating frequency of 5 MHz, 8 MHz or 10 MHz. So it is based on the versions of 8086. And so coming to the pins that are available in the 8086 microprocessor, so totally 40 pins are available. So all the 40 pins of 8086 microprocessor which are arranged in the dual inline package, they can be classified into three groups. Okay. So what are the three groups means? Some signals have common functionality in the minimum mode and maximum mode, whereas some signals have special function in the minimum mode and some signals have special function in the maximum mode. Now we will see what are all the signals having common functionality and which signals have different functionality in the minimum mode and maximum mode. And we will discuss about the function of all the pins in 8086 microprocessor. Now, So this is the pin diagram of 8086 microprocessor. So here you can see some of the pins that comes under common function. That means the signals having common function in the minimum mode and maximum mode. Like, so here you can see from pin number 1, 2, 3, so on up to 20. Okay. And the pin number from 21 to 23 and the pins from 32 to 40. So all these pins will have common functionality in the minimum mode and maximum mode. Okay, 8086 microprocessor operates in two modes, minimum mode and maximum mode. So all the signals from 1 to 20, 21 to 23 and the signals from 32 to 40. These signals will be having common functionality, same function when it is operating in minimum mode and maximum mode also. But here we can see these signals. Okay, so the signals from 24 to 31. These signals will be having different function in the minimum mode and different function, special function in the maximum mode. So for example, if you see this QS0, okay, QS1, S0, S1, S2, log, request and grant. So all these signals, they are minimum mode signals. These signals are called minimum mode signals. Okay. Again, here again from the pin number 24 to 31, the same pins have another function also, that is INTA bar, that is interrupt acknowledgement, ALE, that is address latch enable, DEN, data enable, DT by R bar, data transmit and receive, M by IO bar, that is memory and IO, write, HLDA, it represents hold acknowledgement, and this HOLD, which represents hold. So all these signals, they are called maximum mode signals. These signals are called maximum mode signals. Okay, so totally this all the pins are classified into three types. The pins have common function in the minimum mode and maximum mode. The pins have, these are all the pins, have different function in the minimum mode, and these pins have different function in the maximum mode. Now we will discuss about all these signals. Now, so coming to the pin configuration of 8086 microprocessor, here this pin number 1, it is ground, okay, and here pin number 20, this is also ground signal. So in 8086 microprocessor, totally 2 ground pins are there. 2 ground pins are available. Okay. So in this 8086 microprocessor only, we will have 2 ground pins. So the purpose of these 2 ground pins is to cancel the noise. To cancel the noise. Okay. So totally here in the features of 8086 microprocessor, we have studied that there are multiplexed address and data lines. Okay. So here the pins from AD14 to AD0 and also this AD15. Okay. So this AD0 to AD15. So this is AD0 to AD15. All these pins are available. So these pins are called multiplexed address and data lines. Okay. So these are all the multiplexed address and data lines available. So in this pin configuration, that means here the same signal will be carrying the address and the same signal will be carrying the data. So when it will carry the address and when it will carry the data means it will be dependent on the signal which is called ALE. Okay. So here this ALE means the signal, address, latch, enable. Okay. So in this address latch enable, generally all the latches will be present. Okay. So when this ALE signal is 1, it will be acting as address lines. So when this ALE signal is 0, it will be acting as the data lines. Okay. So this ALE means address latch enable. So here in this the latches will be present. Okay. So here the latch is here nothing but D flip-flop. Okay. So generally we know the purpose of the D flip-flop here. So you will have D, Q, Q bar. Okay. And along with this, you will also have a clock signal. And here this clock signal will be given as input. Generally, how the clock signal will be? The clock signal will be like this. Okay. So here this clock signal consists of 4 parts. So this is one part. Okay. So this part is called negative level. And another part of the clock signal is this. Okay. So here this part of the clock signal is called positive edge. Positive edge. And the next part of the clock signal, this is the next part of the clock signal. Okay. So this part of the clock signal is called positive level. And this is another part of the clock signal. So this part of the clock signal is called negative level. Okay. So here for this flip-flop, when negative edge of clock signal is given. So in this case, when negative edge of the clock signal is given to this flip-flop, D flip-flop, so whatever you are giving across this D, the same thing will be transferred to this Q also. That means if you are giving, for example, D as 1, Q also will be equal to 1. If you are giving D as 0, then Q also will be equal to 0. That means whatever you give, the same output will be coming only during negative edge of the clock signal. Okay. So this latches and all will be present in the address latch enable. So when this ALE is 1, the signals will be acting as address lines. And when this ALE is 0, the signals will be acting as data lines. Now, so here, this is what about the address and data multiplexer lines and ALE signal. Next. So coming to the next signal, it is NMI. Okay. NMI represents non-maskable interrupt. So totally here, there are 2 interrupt signals available in the 8086 pin configuration. So the 2 interrupt signals are here INTR, that is interrupt request, and another one is NMI. So NMI represents non-maskable interrupts. So if any external interrupts are coming through this, coming to the 8086 microprocessor, they will be coming through this NMI pin or INTR pin only. So totally 2 interrupts are only available in 8086 pin configuration. And next signal is here 19th signal. It is clock signal. Okay. So clock signal, that means we have studied in the features in 8086 microprocessor. Clock frequency is 5 MHz, 8 MHz and 10 MHz based on the versions. So in order to produce the clock frequency to 8086 microprocessor, generally we prefer oscillators. Okay. So here the oscillator will be producing the frequency. So the oscillators that are going to generate the frequency, number of oscillators are there. So we have Hartley oscillator, Colpitt's oscillator, LC oscillator. So though there are number of oscillators that are producing the frequency, but out of all those, we will be preferring the crystal oscillator only in order to produce the frequency for 8086. Why? Because crystal oscillator is having the high stability compared to the remaining oscillators. That is why crystal oscillator is used in order to produce the frequency for 8086 microprocessor. And next signal is reset signal, which is used to reset internally the 8086 microprocessor. So all the registers will get reset and again they will be initialized. And next signal is ready signal, test bar. Okay. And next one is RD bar. So RD bar represents read operation. So 8086 microprocessor will read the information that is available on the data bus through this RD bar signal only. Okay. So here in this pin configuration, we can observe for some of the signals, there is a bar like this indicated on the top. Okay. So all the signals that is having bar on the top, they are called active low signals. They are called active low signals. They will be enabled when they are made active low. Okay. And next one is Mn by Mx bar. So Mn represents minimum and Mx bar represents maximum. So here this pin is mainly used because in 8086 microprocessor we have two operating modes. One is minimum mode and maximum mode. So in order to operate 8086 microprocessor in the minimum mode or maximum mode, this pin will be used. Mn by Mx bar. So one of it is active high signal minimum and Mx bar it is maximum mode active low signal. And next signal is BHE bar by S7. So BHE represents bus high enable, whereas the S7 signal, it is multiplexed with S7 signal. This S7 signal represents the status information. And so here, the number of address and data multiplexer lines are only from AD0 to AD15 because only data bus available is 16-bit. But here, the address bus available is 20-bit. That is, the address lines from AD16 to AD19, they are not multiplexed with data lines, but they are multiplexed with status lines. Okay. Now, so here, before going to the detailed discussion about all the signals, we have to learn about the bus cycle. So generally, in order to execute any instruction, the microprocessor requires 4 clock cycles. Okay. So the 4 clock cycles are T1, T2, T3 and T4. So for example, if the instruction is lengthy, if it is not executed in time, we can use wait states also before T4 if it is required. Okay. So, but here coming to the bus cycle, this is called bus cycle. Okay. So here 1 clock period of any microprocessor is called 1 T state. Okay. So 1 clock period of any microprocessor can also be called as 1 T state. And next, so here bus cycle. So the bus cycle consists of 4 clock periods. So here bus cycle, it is 4 T states. So it consists of 4 T states, that is T1, T2, T3 and T4. So in this case here, for example, to read or write data, we require address and data bus. Okay. So if you wanted to read or write the data, we require the address bus, data bus, and also some sort of control signals. And also some control signals. Okay. So here, generally, in order to do this, we require 3 steps. So first is, it has to fetch the information by using the address bus. So what are the 3 steps here means? First one is identify the device. First it has to identify the device from, that means it has to identify the device, whether it has to read or write the information from the memory or from the device. Okay. So first thing is identify the device with its address. Identify the device with its address. So after identifying by using the address where the instruction is, then that particular data should be read. Okay. So here, after identifying the address, after identifying the device with its address, next is generate the control signals. Generate the control signals. So we know that here the control signals will be having the read and write operation. So this is the second step that should be performed. And the next one here is, next step is transfer data through data bus. Okay. So after the control signals have been generated, next step is it has to transfer the data by using the data bus. So these are the 3 important steps that should be followed. Okay. So here, coming to the pin configuration of 8086 microprocessor, it consists of both address data multiplexer lines as well as address status multiplexer lines. Okay. So in which T state the address information is available and in which T states the data or status information is available. Okay. So in both the cases, that is address data multiplexer lines or address status multiplexer lines, only during T1 state the address information will be available. Okay. So here in first T state. Okay. So here the first T state can also be called as T1. So in this T1 state, we have AD15 to AD0 and also A19 to S6 and A16 to S3. Okay. So in the first time period T1, though we have this address data multiplexer lines and address status multiplexer lines, they will be used to carry address. Okay. So during T1, it is used to carry only the address. Whereas here the remaining time states, the data information or status information can be carried. Okay. So in the remaining T states, okay, so that is here T2, T3 and T4. If we use TW, including TW. So in the remaining T states, data or status information is carried. Okay, so data or status information will be carried. So before going to discuss about all the signals in 8086 microprocessor, we need to know about this bus cycle. Okay, so this is what the information about the bus cycle. Next. So here, coming to as we have seen, all the signals have been classified into different types. So first we will discuss about the signals that have the common operation, same common functionality in the minimum mode and maximum mode. So here the first signal is AD0 to AD15. Okay, so this AD0 to AD15, they are called multiplexed address data lines. Okay, so multiplexed address data lines. Now, so especially they are called time multiplexed address and data lines. Now, so these are the multiplexed lines. In order to demultiplex means in order to have only single function, that means whether it has to carry the address or whether it has to carry the data, it will be set by another signal which is available in the pin configuration of 8086, which is called ALE. So ALE stands for address latch enable. Okay. So just now we have discussed about ALE, address latch enable, and the latch present in that signal and the function of that latch. Okay. So here, by using this ALE signal, address latch enable, if this ALE signal is high, it is going to carry the address. That means the signals will be acting as the address lines. And if ALE is 0, that signals will be acting as data lines. That means the data will be carried. Just we have discussed about the bus cycle of 8086 microprocessor. Okay, so recalling that bus cycle, here in this address data multiplex lines, during T1 state, the address information is available, whereas in the remaining T states, the data information will be available. And so not only the 4 T states, T1, T2, T3 and TW, if we want to insert wait states, the wait states can also be inserted, but they have to be inserted before T4 state. Now, so these lines are active high and float to the TriState during interrupt acknowledgement and local bus hold acknowledgement cycle. Okay, so first here entering into the TriState means here we have to discuss about TriState buffer. Okay, so TriState means 3 states. So here this is a buffer having the 3 signals. Now here this is the control signal. It may be 0 or 1. This is the input and output. So for this TriState buffer, for example, if C is equal to 1, the normal operation will be performed. Okay, so what is meant by normal operation means, for example, if you are giving 0 as input, it will be producing the 0 output. So if you are giving 1 as the input, the buffer will be providing 1 as the output. That is, 1 C is equal to 1, it will be giving the normal operation. And here, if C is equal to 0, what happens means buffer will enter into TriState. Okay, so when C is equal to 0, buffer enters into TriState. Okay, so TriState is nothing but, we can also call it as high impedance state. Okay, so it is also called as high impedance state. High impedance state. So high impedance state means almost it will get open circuited. Okay, so these lines, they are active high and it will be floating into the TriState only during interrupt acknowledgement or local bus hold acknowledgement cycle. Now, so coming to the next signals here, they are the 16 address data multiplexer lines. but address lines are 20. The remaining address lines, that is from A16 to A19, they are multiplexed with the status signals, that is S3, S4, S5 and S7. So they are called address status multiplexed lines. Okay. Now, so same as address data multiplex lines, during T1 cycle, here they will be acting as address lines. Okay. So especially here the address lines are from A16 to A19. So they will be acting as most significant address lines. And during the remaining time cycles or bus cycles, remaining time states, they will be acting as the status lines, which carries the status information. Okay. Now, here the status of interrupt enable flag bit is updated at the beginning of each clock cycle. Now, so coming to the status signals which are multiplexed with the address lines, they are from S3 to S6. But here the status lines S3 and S4, these are the two status lines which decides the segment register. So generally in 8086 microprocessor, we have 4 segment registers. Data segment, stack segment, extra segment, and here see 4 segment registers: extra segment, stack segment, code segment and data segment. Okay. So which segment register should be selected? It will be decided by the two status signals S3 and S4. Okay. So if it is 00, extra segment is selected. If it is 01, stack segment is selected. If it is 10, code segment is selected. If it is 11, data segment is selected. So especially this S3 and S4 is meant for selecting the segment registers. And coming to the next status line S6, it will always be 0. And here the next status line is S5. So this S5 says the condition of the interrupt flag. Okay. So this interrupt flag is one of the bit available in the flag register format of 8086. So this S5 represents the condition of the interrupt flag. That means whether that interrupt flag is set or not. Now, so here also, since these address and status lines are multiplexer lines, in order to demultiplex that address and status lines, the same ALE signal will be used. Okay. So like when ALE is 1, they will be acting as address lines. Okay, they will be carrying the address. When this ALE signal is 0, they will be carrying the status information. Now, the next common signal is BHE bar by S7. So here it is indicated like that, or it can also be indicated as BHE bar. Okay. So this BHE bar is active low signal. So BHE bar stands for bus high enable. And this S7 represents the status line. Now, so this bus high enable signal indicates the transfer of data over the higher order data bus, that is from D8 to D15. And it is used to enable the higher order data bus. So generally the data bus is 16-bit. Especially this BHE bar is used to transfer the data by using higher order data lines only. Now, so this BHE bar will be enabled only during the higher order address lines. So since it is active low signal, in order to enable that, it should be made as 0. Now, so during time states, this BHE bar is low during T1. Okay. for read operation, write operation and interrupt acknowledgement cycle. But whenever a byte is to be transferred on the higher byte of data bus, this is only during T1. But here, during the remaining time states, that is from T2, T3 and T4, the status information will be available. Okay. So, any signal, if we are discussing, we have to talk about the relation with the bus cycle. That is during T1, what is the function, and in the remaining time cycles, that is T2, T3, TW and T4, what is the status, that is what is the function. Now, so the signal is active low and tri-stated during hold signal. Next, so here this S7 is one of the status signal which is combined with that BHE bar signal. So this S7 will be always 1. Now, so this BHE bar signal along with this A0, it will decide which address it is going to select. Selection of the address. Okay. So here if this A0 and BHE bar is 00, whole word will be transferred, and this 01 upper byte or odd address, if it is 10, lower byte from or to the even address, and if it is 11, it is not valid. Okay. And the next common mode signal is RD bar. This RD bar represents read. Okay. So this is RD bar. So it is active low signal. It is active low signal. Okay. So here by using this RD bar signal only, the microprocessor is going to read the information from the IO device or from the memory. Now, so this RD bar signal will be active low during T2, T3 and TW cycles. And the next common signal here is ready signal. Okay. So this ready signal is the acknowledgement that is coming from the slow devices. Okay. So if ready signal is activated only, the data transfer will be performed. So if the ready signal is not activated, in order to perform the data transfer, we have to wait unless the ready signal is activated. So in order to wait such that the ready signal is activated means we have to insert the wait states during the bus cycle. And next common signal is INTR. So INTR is one of the interrupt signal available in 8086 microprocessor. So this INTR represents interrupt request. INTR represents interrupt request. Suppose if any devices wants to request 8086 microprocessor its service, they will be requesting the microprocessor through this interrupt request only. Okay. Now, so if any interrupt request is pending, the microprocessor enters the interrupt acknowledgement cycle. So this signal is active high and internally synchronized. And next signal, common mode signal is here, test bar signal. So this test bar signal is active low signal. Now, here the input is examined by including the wait instruction. Now, for example, if the test pin goes low, that means already it is active low signal. It will be activated when the signal goes low. Okay. So, for example, if the test pin goes low, the execution will continue. Okay. So, in another case, the microprocessor will be ideal. That means it is not going to execute any instruction. It will be executing any instruction or it will do any operation only if this test bar pin goes low. And This input is synchronized internally during each clock cycle on leading edge of the clock. And the next common signal is NMI signal. So NMI represents non-maskable interrupt. Okay. So non-maskable interrupts means the interrupts that cannot be disabled. That means if any interrupts are coming through this NMI pin, they are called non-maskable interrupts. Another name of this non-maskable interrupts can also be called as type 2 interrupts. Okay. So here a transmission from low to high initiates the interrupt response at the end of the current instruction. Here this interrupt will be internally synchronized. Now coming to the next common mode signals, it is reset. So it is active high signal. When this reset signal is activated, the 8086 microprocessor will get reset. Okay. So getting it reset means, what happens means it terminates the current activity whatever it is doing, and again it starts execution from the beginning once if this reset signal is activated. Now, so the signal is active high and must be active for at least each 4 cycles, because the bus cycle requires 4 time states. It restarts the execution when the reset returns low. So it will also be internally synchronized. And the next signal is here, clock signal. So the clock frequency required for 8086 microprocessor is based on the versions 5 MHz, 8 MHz and 10 MHz. But here there are number of oscillators that will be producing the clock frequency like LC oscillator. Okay, but here out of all these oscillators, only crystal oscillator is preferred in order to produce the frequency, because it is having the high stability. Because of high stability, the crystal oscillator is preferred. Okay, so here the clock input provide basic timing for the processor operation and bus control activity. So for 8086 microprocessor, whatever we are using, generally it will be having 8 MHz frequency. Now, the next common signal is VCC. So VCC represents power supply signal. So generally here the microprocessor requires plus 5 volts power supply, that too DC power supply only for the internal circuit operation. And next signal is ground. Okay, so here in 8086 microprocessor, generally we have 2 ground signals, not 1. Okay, so 2 ground signals in order to cancel the noise, and it is ground for the internal circuit. Coming to the next classification of the signals, that means the signals coming under minimum mode pins. The first signal is here INTA bar. Okay, so INTA represents interrupt acknowledgement. Interrupt acknowledgement. Okay, so here this INTA bar and INTR, these two are the handshaking signals. So whenever any interrupt comes through INTR signal, the microprocessor will send the response to that requested device through this INTA bar, that is interrupt acknowledgement signal only. So to understand that the particular interrupt has been accepted. And next signal is M by IO bar. So this is active low signal. Okay, so here the reading or writing operation can be happening from the memory or from the IO device, or to the memory or to the IO device. So here M by IO bar represents memory or input output. Okay, so here M is the active high signal and IO bar is the active low signal. So when this M by IO bar signal is 1, it indicates memory operation. That means reading or writing operation will be performed with the help of memory. And when this M by IO bar is 0, it performs the IO read and write operations. And next signal is WR bar. So WR bar represents write operation. Okay. So this is active low signal. The microprocessor will read the information from the memory or from the IO device by using this WR bar signal only. And the next minimum mode signal is DT by R bar. So DT stands for data transmit and receive. So here transmit is the active high signal and receive is the active low signal. Okay. So transmitting and receiving is nothing but reading and writing. So transmitting means writing, receiving means reading. So the microprocessor will read or write the information by using this data transmit and receive signal. Okay. So during reading operation, the data receiver will be activated. During writing, the data transmitter signal will be activated. So data transmission is active high and data receive is active low. So if DT by R bar means data transmit, if DT by R bar is 0, it represents data receive. And next one is DEN bar. So it is data enable. So this data enable is active low signal. So when it is enabled, it represents whether a valid data information is available on the data bus or not, and whether it is transferred it or not. Okay. And the next signal is ALE signal. So ALE represents address latch enable. Okay. So already we have discussed about this ALE signal, address latch enable. We have different address and data multiplex lines and address and status multiplex lines. So in both the cases, when ALE is 1, address information will be carried, and when ALE is 0, data information or status information will be carried. And the next minimum mode signals. The minimum mode signals are hold signal. So generally here, hold signal means if any master wants to request the system bus access to 8086 microprocessor, it will be requesting the system bus access through this hold signal only. And next signal is HLDA. So HLDA represents hold acknowledgement. Hold acknowledgement. Okay. So whenever the microprocessor receives the hold signal, it is going to send the acknowledgement through the hold acknowledgement signal, saying that it is going to release the system bus access in the next bus cycle. So this hold and hold acknowledgement, there are two handshaking signals. And next maximum mode pins are MN by MX bar. So this MN is active high signal, whereas this MX bar represents active low signal. So MN stands for minimum and MX bar stands for maximum. Okay. So as this 8086 microprocessor is having two modes of operation, when this MN by MX bar signal is equal to 0, it will be operating in the maximum mode. And when MN by MX bar signal is 1, it will be acting in the minimum mode. So making this signal equal to 0 means we have to connect this MN by MX bar signal to the ground. And making this MN by MX bar signal to 1 means we have to connect that MN by MX bar signal to VCC. And next signal is here lock bar. So it is active low signal. Okay. So when this lock bar signal is activated, the system bus will be locked. So though there is any request for the system bus by other masters, if once this lock signal is enabled, the microprocessor or any requested device cannot give or take the system bus because the system bus will be locked. Now, the next maximum mode signals are S0, S1 and S2. Okay, so all these are active low signals. So they are called status signals. They are called status signals. So generally, these status signals will indicate the type of operation that is carried out. That means whether read operation, write operation, okay, whether it is from the memory or from the IO device. So all these type of operation will be decided by these three status signals. So here S0, S1, S2. So for example, if these three are zeros, the type of operation that is performed by the processor is interrupt acknowledgement. If it is 001, read from the IO devices. If it is 010, the operation is write to the IO devices. If it is 011, the operation is halt operation. If it is 100, the type of operation is code access. If it is 101, the type of operation is read from the memory. If it is 110, the type of operation is write to the memory. If it is 111, the type of operation is passive. So these three status signals will decide the type of operation, and they are active low signals. And next maximum mode signals are RQ1, GT1 and RQ0, GT0. So they are called request and grant signals. Okay. So though you have this request and grant, two signals are there. Okay. So why? Because this is maximum mode. Multiple processors can be connected. So you will have two request lines and two grant lines. Okay. So here this though there are two request and grant lines, among these two, this RQ1 and GT1, so this will be having the low priority, whereas this RQ0, GT0 will be having the high priority. Okay. So if any other masters wants to request the system bus, if it is in the maximum mode, they will be requesting the system bus access through this request lines only. And if 8086 microprocessor is willing to release the system bus access, it will be sending the acknowledgement through this grant signals only. Okay. So, but whereas in the minimum mode signals, the same bus for the system bus, request and grant will be done by the two signals, hold and hold acknowledgement. But here in the maximum mode, that bus request or access of the system bus in order to ask by other masters, they will be through the request and grant signals. They are bidirectional pins. That means the same signal will be acting as request signal, same signal will be acting as grant signal. And next maximum mode pins are QS0 and QS1. They are called Q status lines. Okay. So these lines says the status of the Q. So already in 8086 microprocessor, we know that in the architecture we have studied, it is having 6-byte instruction queue. Okay. Now, so based on this QS0 and QS1 signals, it decides the queue operation. So when these two signals are 00, no operation. When it is 01, first byte of opcode from the queue. And if it is 10, the queue is empty. And if it is 11, subsequent byte from the queue. So these two signals represents the queue status. So this is what the pin configuration and signal description of 8086 microprocessor. And we have studied the function of each pin that are available in the 8086 microprocessor pin diagram. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.